Hey everyone, it's your favorite math celebrity, Mr. Martin. Woo woo! All right, hey. Hey, I miss you. I hope you're having a good day so far, and make sure you thank Mrs. Christian for being with you today as your math teacher. Here we are. So we got 16.5. We're talking about probability models, which is just a mathematical way of representing some sort of random phenomenon. All right, like flipping a coin at random or spinning a spinner, like in this situation. So key concept, a probability model is going to consist of an action such as flipping a coin, or in this case the action is spinning the spinner once, right? One spin of the spinner. It also consists of the action sample space, which again is that list of all the possible outcomes that could possibly occur. So you could get a red, there's a red, you could get another red, there's a red there, here's a blue, you could get a blue, you can get another red, or you could get the final blue, right? Those are all the possible outcomes. That's called the sample space. It also needs to include a list of all the possible events and their probabilities, right? So here's an event that could occur. One event, what's the probability of getting red, right? And there are 1, 2, 3 reds out of 1, 2, 3, 4, 5, right? So the probability of getting red is 3 out of 5 for this spinner. Probability, another event, probability of getting blue is 2 out of 5, right? 2 out of 5. Okay, so those are the two events that occur. There's no other event that could occur, right? We can't get both blue and red at the same time. We can't get green, yellow, and so on, right? So these are the only two events. The events and the probabilities in the list have to meet these requirements right here. Each outcome in the sample space is in exactly one event, and this is really important as well, the sum, when you add all the probabilities together, it must be 1. So we've checked our work over here already. Probability of getting a red is 3 out of 5, so there's 3 out of 5, and if you add to that the probability of getting a blue, 2 out of 5, you'll end up with 5 out of 5, which is equal to 1 whole, which is, as you know, equal to 100%. Right? So when you spin this spinner, there's a 100% chance you're either going to get red or blue, right? So that's really important. These are the two incredibly important requirements that you have to have in order for a probability model to exist. Okay, so moving on to part 1, it says which list of probabilities does not complete a probability model for this action. So in other words, which list does not meet both of those requirements from above? Both of these requirements. So which of these lists does not satisfy both of those? Let's check. So here's our action, just choosing one card. And here's our sample space. These are all the possible cards that we could choose from. Okay, so list 1 says, what's the probability of getting fewer than 3 shapes when you choose one card? Fewer than 3 shapes. Well, here's 1. That's fewer than 3 shapes. That's 1. That's fewer than 3 shapes. That's 2. That is 3 shapes. These are more, so we're not going to include any of those, right? So the probability is 2 out of 1, 2, 3, 4, 5, 6, right? So that's 2 out of 6, which they reduce to 1/3. Okay, and then the probability of another event occurring, like getting at least 3 shapes, which means it could be 3, could be 4, 5, or 6, would be, as you know, 4 out of 6, which is equal to 2/3. We want to see, does this list satisfy both requirements from above? All right. Does each outcome in the sample space, is it exactly one event? Yes, it's one event. And then, is the sum of all the probabilities equal to 1? When we add 1/3 plus 2/3, does that equal 1? And we can double check that 1/3 plus 2/3 is equal to what? Right? 3 out of 3, which is equal to 1 whole. So this list is good. Wow, my light's turned off. There it is. Oh my goodness. Sorry guys, that was so scary. Oh my. Here I am alone in my classroom after school making this video, and the light goes off. All right. Sorry guys, here we are, moving on. So list 1 is actually good. The question is, which list of probabilities does not complete a probability model? This one does. This does. Beautiful. Happy face. Hooray. Oh, there's the happy face. Okay, what about list 2? Let's check that out. Probability of getting a fish. Here's one fish. Those are apples. These are apples. These are fish. These are leaves. I know it's hard to see. These are apples. Probability of getting a fish. There's 1, 2 out of 6, right? 2 out of 6. All right, and so on. And they give us actually all of these probabilities, and these are all accurate. They're already done for us. You could double check them if you wanted, but probability of giving apple, that's going to be 3 out of 6 because that's half of them, right? So 1, 2, 3 out of 6. And then same thing with leaf. There's only 1 leaf right there out of 6. All right, so we want to see if we add 2 6 plus 3 6 plus the 1 6, will we end up with 1 whole? Yes, we do. This does complete a probability model, so that's a good thing, but it's not good for our answer because we're trying to find which one does not complete. So that's not an answer. List number 3. Here we are. Probability of getting an even number of apples. Even number of apples. 1. That's not an even number. That's an odd number. And then 2, 4, 6. That's an even number. So that's 1, 2 out of 6, which is where they got the 1/3 from. Probability of getting an odd number of apples. That's even. This is odd. That's the only odd number of apples. That's 1 out of 6. But does 2 6 plus 1 6 equal 1 whole? Sure doesn't. Correct? All right. So this is not a probability model, and we're abbreviating for the sake of time. All right. This is for that reason. It does not satisfy both of these requirements from above. The sum does not add up to 1, and it needs to in order to be an accurate probability model. Moving on to the back. Here we are. A probability model based on using the theoretical probability of equally likely outcomes, where everything has an equal opportunity of happening, is called a uniform probability model. All right. Before setting up a probability model, you can ask yourself, well, can I use theoretical probability? Are the outcomes equally likely to occur? And therefore, I can use a uniform probability model right here. Or do I need to actually collect some data and use relative frequencies like we learned about yesterday in the Skittle lab in order to actually make a more informed decision? Can I go with theoretical probability, or do I actually have to gain some data in order to make a better decision about what's really going to happen in whatever event, whatever experiment is about to happen? So here are some examples. Tell whether you can use a uniform probability model for each situation, and then explain your reasoning. Situation A, a city planner wants to know the probability that a car waiting at a stop sign will either turn left, go straight, or turn right. They want to know, can they use a uniform probability model to represent that? Well, a city planner who wants to know the probability that a car is waiting at a stop sign, whether or not they'll turn left, go straight, or turn right, I mean, we don't really know whether they're going to go left, straight, or right. And it's really not a random thing, because what if off to the left you got this huge mall down here that everybody wants to go to? It's got great stores, it's got great restaurants, like everybody wants to go there. What if going straight is nothing, just like farmland where people really don't want to go? No offense to you farmers or people that ride horses. Anyway, what if, to the right is some other fantastic thing like Kings Island or something that people really want to go to? The probability of somebody turning left to go to the mall or go straight to go to this random farm that nobody wants to go to, or Kings Island, those are not the same. It's not a uniform amount that's equal, right? People would probably want to go over here or over here, turn left or right before they'd... Oh, that's supposed to be a sad face. Oh my goodness gracious. Terrible, terrible. Oh gosh. Allison, I know you're going to love that one. Adelie, I know you're going to love that one too. Anyway, right. Okay, so this is not an opportunity for you to use a uniform probability model. No, because we don't know, and this is what we should write down in our notes. No, we cannot use a uniform probability model because we don't know that each turn is just as likely to be chosen as the other. Right? They might be more likely to turn left because there's the mall over there, or more likely to turn right because there's Kings Island or whatever it is, right? So there's not an equal chance of turning left, right, or straight. All right, therefore we cannot use a uniform probability model for this situation. Situation B, though, two friends on a walk are playing a game, and then at each intersection they choose at random, completely randomly, from 3 slips of paper. They choose randomly to turn left or go straight or turn right, right? Like out of a hat. And then that's the way they turn. So is this a situation in which you could use a uniform probability model? As you might say, yes. Yes, it is. Because what is the probability of turning left, right, or straight? Because the probability of turning left is, what is the probability of turning left if you're choosing from these 3 options at random, like out of a hat? Right? As you know, that's 1/3, right? Turning right is also 1/3, and turning, well, really just going straight is also 1/3. So you have an equal opportunity of going left, right, or straight. Why? Because they're choosing at random. That's incredibly important. Okay, so therefore you can use a uniform probability model here, and that works. All right, last thing, moving on. It's 12 minutes long. Let's get going. Here we go. The table shows data collected from 4 cashiers in a grocery store. Write a probability model to find the probability that a customer will use each type of bag down here. These are answers to the question, hello, sir, what type of bag would you like me to bag your groceries in, right? Like they do at the grocery store. 252 customers are requesting plastic. 21 customers are requesting paper, and then 77 are saying, oh no, I'm just going to use reusable bags. We need to create a probability model to find the probability that a customer will use each of these types of bags. So, probability of choosing plastic. What's the probability of choosing plastic? Well, 252 will be the numerator, because that's how many chose plastic, out of what usually goes down here, right? The total of all of these, 252 plus 21, that's 273. 273 plus 77 should be 350, if my math is correct. 273 plus 77, that should be 350. Okay, and if we actually divide that out, I'm going to have to come back to that because I forgot my calculator. Sorry, guys. Here we are. Let's do the next one. Let's come back to that later. Let's figure out what percent that is later. Or you could do it right now. You do it right now. 252 divided by 350. Here we are. It's 0.72. Hopefully you got that, which is what percent? 72%. Good. 72% of the people are requesting plastic, right? What's the probability of somebody choosing paper? Same logic, 21 people chose paper out of how many? 350, right? 21 divided by 350, as you know, is 0.06. What percent is that? Don't get tricked. It's not 60%, it is 6%. Chose paper. And then lastly, the probability that someone would choose reusable bags would be equal to 77 out of 350, which is equal to 0.22, which is equal to 22%. The question is this a good probability model? What do all of these percents have to add up to? Yes, 100%. And does it? 72 plus 6 is 78%. 78 plus 22 is 100%. Right, and you would also find that 0.72 plus 0.06 plus 0.22 is also equal to 1.0, right? 252 plus 21 plus 77 should be equal to, yeah, 350 out of 350. I'll write that up here. All right. So probability models have to satisfy both these requirements from